your alloy composition is given by Ni. That is
in between
say this here this composition whatever I drew before, say that is Ni. So you were here before, suddenly going to here, and at that temperature this gives free energy per atom. This is gives y-axis is gives free energy per atom. At that temperature of T, this plot of gives free energy per atom versus composition. So in book you will see that the composition of mole fraction is given in terms of capital N in place of X. So you just tell me which one I should follow for this class, X or in
X.
X. Be consistent. Majority wants X or N? So if you see in book, whatever capital N is just nothing but mole fraction X. So never get confused by the difference in notations. So I wanted to say that this is Xi. Initially I wrote Ni, so Xi. That is your alloy composition. Xi. Now, if because of fluctuation in composition and embryo of certain composition, say here, given by Xn forms. One small embryo is forming, you have come down, you have points to a temperature of a alloy composition of Xi. At that temperature, when you came down here, what is the gives free energy of that just after quenching is given by this. So gives free energy of this is say Gi. Gives free energy per atom is given by that point on the curve Gi. Please pay attention, everyone. David, please pay attention. Everything is in the book, but your life will be much easier if you can follow this, and then you do not need to even read. But still, I am explaining, it will be easy for you. So this is your gives free energy just after quenching. But if you give enough time, this will form another product, and the matrix phase composition will come to this composition, and product phase composition will come to this composition. Okay. And so then the final gives free energy will be on this point. So final gives free energy will be given by this. Just after quenching, your gives free energy is Gi. Now, if an embryo of certain composition, say, let us keep the embryo composition as variable. Say somewhere here Xn is formed. For formation of that embryo of composition Xn, your alloy composition, matrix composition will change to a certain lower value somewhere here. Say that composition is X1. Because of formation of an embryo of composition Xn, your matrix, because a small embryo has formed, So your matrix composition will come down a little bit. So x1 is very close to xi, but it is just lower than xi. At that point, your Gibbs free energy of the matrix is given by this point, which is G1, and Gibbs free energy of your embryo is given by Gn. So your Gibbs free energy of the system will lie at that point, which is the intersection of this vertical line given by pink and this line joining these two Gibbs free energies, Gn and G1. So this point just below Gi will be your Gibbs free energy of the system with the matrix of composition x1 and one embryo of composition xn. So what your Gibbs free energy, what is the total Gibbs free energy then? Fraction of embryo multiplied by Gn, fraction of matrix multiplied by G1. This is your Gibbs free energy of that at that moment of the system. What is the change in Gibbs free energy? This minus Gi. So fraction of matrix, Gibbs free energy of matrix is given G1, fraction of embryo, Gibbs free energy of embryo, that is your Gibbs free energy at that point. What is the change in Gibbs free energy? Minus Gi. Okay? So this is the change in Gibbs free energy. Change in Gibbs free energy per atom of precipitate will be 1 over fraction of precipitate, say embryo or precipitate. So this is Gibbs free energy change in Gibbs free energy per atom of precipitate or embryo is given by this. And if lambda is volume of an atom of an embryo, then Gibbs free energy change per unit volume of an embryo is given by this. Yes or no? Everyone followed this. This is your Gibbs free energy of the system per atom minus your initial just after quenching before it before the embryo form. That is the change in Gibbs free energy. You have this much fraction of atom in that one, per atom of this is delta G per atom of the system. In that per atom, this much is the precipitate. So per atom of precipitate Gibbs free energy change is this one. And if this is the molar volume or volume of an atom in a precipitate, then this is the Gibbs free energy change per unit volume of precipitate. Everyone is clear in this? Now what is Fm? From Lever rule you have to say, David, what is Fm? What is Fm? Fm is the fraction of matrix. From Lever rule, can you say from this diagram? you have an embryo of this composition, you have your overall alloy composition is this, your matrix composition is this. What is the fraction of an embryo from using Lever rule? So this divided by this length, xi minus x1 divided by xn minus x1. Yes?
Lambda is a molar volume.
Yes.
Molar volume
Or lambda is the volume of an
atom.
mean volume per atom is the average volume per atom of the precipitate, because this is gives free energy. Listen, small. This is gives free energy change per atom of precipitate. Lambda is the average volume of the average volume per atom of the precipitate. That's why we are getting gives free energy change per unit volume of precipitate. Should I write those things? Gives free energy change per
Atom per
unit volume per unit volume of precipitate. Precipitate or embryo. This is fraction of embryo. This is fraction of matrix. This is just a gives free energy change per atom. Now gives free energy per atom after the embryo has formed. This much is gives free energy change per atom of the system after the embryo has formed. So that is a change in gives free energy per atom of the system. And the whole thing after 1 by Fe, it is delta G per atom of precipitate. So lambda is average volume per atom of precipitate. Volume per atom of precipitate. And FM is now your x
xi minus x1
xi minus x1 xn minus x1.
It should be Fe. Then it's Fe.
What is FM and what is that?
xn minus xi
xn minus xi, xn minus x1 put Fe here also, everywhere you put Fe and FM expressions in terms of x to put it on your notebook, the next step. You are just putting this. Can you tell the expression? So if you just rearrange, you just multiply this inside. This will be your, that is 1 by Fe, this is Fe, so it will be just Gn 1 over lambda. If you just multiply and rearrange, you will get inside Gn minus, you just take G1 out and you will get xn minus x1 Am I writing G superscript or subscript as I1? Sometimes I am writing superscript, sometimes subscript. Do not, so those mistakes you correct yourself. So you are getting, just after rearranging this, you will get this one, this step, okay? Now if you note, as I said, that just formation of one embryo of this composition will change your matrix composition very little. So your x1 is very close to xi and your g1 is very close to gi. So if we take that assumption that x1 is very close to xi and your g1 is very close to gi, we can write this equation as, then what will be this one? So gi minus g1 divided by xi minus x1, that is the slope of this curve at xi. You take this bracketed term, I am talking of this bracketed term, gi minus g1 divided by xi minus x1 is nothing but the slope at this point. gi minus g1 divided by xi minus x1. So this is our slope of the curve at xi. This one. And so we can write this as 1 over lambda Gn minus, in place of G1 we will write Gi minus Xn minus Xi del G del X at Xi. Fine. What is this term? Can you just see this one? X. This is the slope multiplied by xn minus x1.
This height.
Xn is here, your x1 is here, or xn minus xi I wrote. So xn minus xi. So this is the difference between difference in composition between your embryo and your alloy. So this length multiplied by the slope will be.
This height.
So if I take a tangent at that point, so this is the tangent. So it is the vertical distance from the tangent till Gi.